morning, students. Welcome to the class of Foundations of Cognitive Robotics. In the last class, we have talked about one of the basic building block for organismoid robots, which is piezoelectric smart material. We have discussed how this piezoelectric smart material, with the help of the direct and the reverse effects, we can build up different types of actuators and sensors which can be very effective in terms of developing some of the parts of these robots. Now, there are certain disadvantages of these piezoelectric materials. One, of course, is that it needs slightly high voltage, and secondly, it is basically a kind of a capacitor in nature. So just like a capacitor gets discharged with respect to time, similarly piezoelectric material loses its efficiency because it gets discharged, and hence it needs to be repoled after certain durations of time. So it can be used for very sophisticated type of actions, let's say for the finger manipulations or for certain motions or rotations, but for more robust and rugged action we need more powerful actuators. Now, one of the most powerful actuators is magnetostrictive actuator. We will discuss about it today. Also, we will talk about some of the artificial muscles that we can develop with the help of another smart material called shape memory alloy. So let us have a look into both of these these two different types of smart materials, the magnetostrictive materials and the shape memory alloy. We will first talk about the magnetostrictive materials, and the name itself is somewhat suggesting you that these are materials which has a magnetic connection. Yes, indeed, that these are materials which responds to the change in magnetic field. So whenever, and the advantage of the magnetic field is that you can essentially generate the changes without physically in touch with the object, which means you can develop the force at a distance because magnetic field can get transferred without a physical contact. So that's the attractive part of it. And the second part, the strictive part in magnetostrictive materials, it essentially refers to that the magnetostrictive material can respond to the change in the magnetic field. So that's what is the stricture refers to. Now, if we look into the availability of magnetostrictive materials, we will see that one of the most popular magnetostrictive material is terphenol D, which is made of rare earth material called terbium and iron, that is the Fe, and it is first developed in Naval Ordnance Laboratories, so that's why their name goes. And of course there is a D which stands for dysprosium. So essentially it is a kind of an alloy of terbium, iron and dysprosium. Now what it imparts, this alloy, is a very high energy density. If you can look at this video of a terphenol D material sample here, and you can see that if it is hit, just impact force, so much of energy gets dissipated from the system. So it has a very high energy density. Now naturally this actually tells us that it will be very good in terms of an actuator. Now how does this magnetostriction happens in these kind of materials? Well, you can think of that as if each of these magnetostrictive element will be having millions of this type of small magnetic domains, just like beads, with its own dipole direction with its own magnetic field directions, which can be random to begin with. So that's what is the general state of a magnetostrictive material when the magnetic field applied is zero. Now the moment from a distance I apply a magnetic field, each one of these magnetic domains, they start to align themselves towards the magnetic field, and you can see as a result the entire group of materials, they actually expand in one direction, creating a magnetostriction in the system. So thus by applying magnetic field you can actually expand, and you can essentially only expand but by playing certain tricks you can also make it contract, and thus you can make a forward and backward movement with the help of magnetic field by using this type of a system. Now there are a whole lot of materials, ferromagnetic materials mostly, which shows this behavior, and initially it was observed of course in iron and nickel by Joule long before in 1880 or so. But today the material, as I already told you, we use, one of them is terbium, dysprosium and iron, and also there is another material in which instead of terbium we use actually gallium. So these materials have large magnetostriction. That means they show large deformation in comparison to, let's say, iron or nickel. So something like 2400 parts per million, that is the level of strain that you will see. Now this is of course a dimensionless quantity, and the other important thing is that it will show these up to a very high temperature, which is good, which means they can really work in a very rugged environment. Now how much is this 2400 or 2500 parts per million? It is, even though it looks like a large number, but in terms of actual change of length it is not that large. In fact, if you look at this curve that we have here, the length of Turfenoldi rod, let us say we consider a 100 millimeter length rod, then with about 2500 parts per million, the change will happen is only 0.24 millimeter. So which is even smaller than 1 millimeter. It may not be visible in the naked eye, but it has actually lot of power, and you can also amplify it just like for piezoelectric material, and then you can make good use of this kind of a system. So the other important thing for the Turfenoldi material is, as I told you, that if I change the direction of magnetic field, no matter positive or negative, you will always get expansion out of it. It always increases. But there are two interesting things to note here, that if you can somehow keep it stressed to begin with, you apply some initial stress, you can get actually larger strain out of the system. And the second thing is that this is how you can get a bidirectional movement. Let us say if you keep it already under a biased magnetic field, let us say somewhere here, then if you increase the magnetic field, it is going to expand. If you decrease, it is going to come down. So which means you can actually get a bidirectional movement out of the whole thing. The only thing that you are sacrificing is that the range of strain in the earlier case, if it is only unidirectional, is quite large, whereas here it will be with respect to the bias, and hence that range will be smaller. It will be about half of what you can get otherwise. So this is what is the famous butterfly curve that one has to keep in mind for designing systems using Turfenoldi. Now the attraction of such Turfenoldi materials are manifold. For example, you can use it for large force generation, up to 50 megapascal stress level you can create. You can create large deflection up to 200 millimeter, and you can get a large energy conversion efficiency, and most importantly it does not decay with time. That's a very good advantage of the magnetostrictive transducer, and it is cost effective in terms of a low frequency band. It's not as high as a frequency band like a piezoelectric material, and firstly it was used in deep sea underwater applications like this Talon. You can see tactical acoustic littoral ocean network. The entire sonar system of Talon is made out of magnetostrictive terphenology materials, which is sourced by Etrima products. Now, I told you about direct and reverse effects, if you remember. The direct effect is useful as a sensor. When you are applying force, you can get the voltage, or in this case a change of magnetization in the magnetostrictive material. That's the direct effect. And the reverse effect is used for the development of actuators, where in this case, as we will be changing the magnetic field, we will be able to see the change in terms of the length of the system. Now, for magnetostrictive material, there are many different effects. You need not only always see the change in length, you can actually generate the change in terms of twisting in the system, or a change in terms of the bulk volume in the system. And similarly, the same material can respond to if there is a twisting happening, or if there is a bulk change of volume that is happening, it can actually respond to that through the change with respect to the change in magnetization. So there are various effects of the magnetostrictive material. Some of the magnetostrictive effects which is used for actuation and sensing are, for the reverse effect, Joule effect is of course there, where there is a change in dimension, but also sometimes we use the Weitmann effect, where a helical magnetic field will create a torque, so that if you have a torque like motion generation system required, you can use the Weitmann effect. And also in some other cases you can use the magneto-volume effect, so that the magnetic field can create a change in volume. And from the sensor perspective, there is Villari effect, which actually responds to the change of stress in the axial direction, and that is reflected in terms of change in magnetostriction. But there is also Matthieusi effect, where if there is a torque, it senses and it sense it in terms of a kind of a magnetic field induced EMF. And there is something which is known as Nagoka-Honda effect, where if there is a change in volume, it actually senses it in terms of a change in magnetic state. So there are three varieties of reverse effects and three varieties of direct effect, which you can use for building up actuators and sensors using magnetostrictive material. Now, the constitutive equation of such materials are actually very similar to the piezoelectric material. As you can see that for the actuators point of view, we will generally use the Joule effect, and in the Joule effect, if you apply the magnetic field through H, you will be able to see the strain, and that's the deformation, and that's the deformation that we can use in terms of either by restricting it so that you get a force, or by change of length of the system. Remember, if there is a change of stress, then also deformation occurs, but that's not like a smart material like behavior, because that happens for any system. For the magnetostrictive material, this actually happens because of, once again, the coupling called magnetomechanical coupling here, like piezoelectric coupling. So here this D actually creates a coupling between H and epsilon, so that if there is a change in H, you get a change in epsilon. Now that is as far as the actuator building is concerned. Similarly, for the Villari effect, if there is a change in stress sigma, then there will be a change in magnetization, which can be sensed in terms of a change of voltage in a pickup coil, etc. And once again, the magnetomechanical constant D plays an important role here, because as the D increases for a material, with a smaller change of stress, you will be able to get a large change of magnetization. Of course, the magnetization can be changed by the magnetic field also, but that is something which happens for a regular solenoid, and it is governed by the permeability, and that is not what we are focusing for a smart material. It is this D sigma part which we will be capitalizing for the development of the sensors for the magnetostrictive material. Now, there are many applications of it. For example, if you want to control the noise and vibration, let us say during the motion of a robot, this is used. Machine tools, if you have controlling of machine tools, controlling of servo valves, just like I told you that so many servo valves are required for, say, for example, the different types of pneumatic actuation. So you can actually use these magnetostrictive material instead of compressor based pneumatic materials. It will be much less bulky. So for servo valves you can use it. You can use it for hybrid motors, for sonar devices, for brake systems, micro positioner, and different types of cleaning and welding type of applications. Now, one of the very common magnetostrictive actuator is called magnetostrictive mini actuator. So if you look at this magnetostrictive mini actuator, in this case you can see that there is a terphenol D rod which is sitting inside, as you can see it here, and then there are these magnetization coils and there is a set of permanent magnet. So what will happen is that the moment I will apply, and because of this permanent magnet is already biased, now the moment I will apply an external magnetic field, then depending on the direction of it, this terphenol D rod will expand or contract, and as a result this piston will move forward and backward, and that can be used in terms of motion generation in a robot for various types of applications. Now here I will show you a very interesting application of magnetostrictive material, and this is in terms of its motion as an earthworm in a conduit. So you can see this is also known as inchworm motion, and there are inside this there are these magnetostrictive materials, and there is a stick slip happening, and because of the expansion and contractions, and you can see that that is happening, and that is creating the stick slips, and the whole thing is actually propagating. So you can make it wired or wireless, but this has excellent applications in terms of development of pipe health monitoring robots. And you see this is an application which is completely wireless, and you see the whole thing is moving vertically. So if you want to, let us say, create an animalistic motion, let's say a kind of an ant-like motion, we can actually miniaturize it, as you can see here that people have even miniaturized such a thing. So a ant-like motion, and inside a conduit, this particular type of robot using magnetostrictive actuator can be very good in terms of generation of such motions, and you can see that how small you can make the whole thing. And here you can see that how nicely it is going inside a pipe, and if you have sensors, it can actually monitor in that case the nature of changes that's happening in the pipe, and it can do that both upward and downward. So you can have a versatile movement that you can generate out of this system. So this is what is about the magnetostrictive material. I told you that we will be discussing about two materials today. One is the magnetostrictive material, and for which I have shown you that their greatest application for our purpose will be in terms of generating locomotions, and that you can do for different very complex environments. You can do it. Of course, you can use such materials for sensors as well, but mostly it is used as actuators. Now, other than these two, there is also a third way of creating motions, which we will discuss today, and that is with the use of certain artificial muscles. Now, one of the artificial muscle category is actually metallic alloys, and it is known as popularly shape memory alloy. So let us have a look into how these shape memory alloys behave, how we can actually use them in terms of actuations, and in some cases as sensors as well. Let us look into the nitty-gritties of shape memory material. So we will look into the smart materials based on shape memory alloys and electroactive polymer, and today we will specifically focus on shape memory alloys. Now, what is a shape memory effect? It is some kind of a memory, right? And it is a memory, as the name suggests, is related to shape. So precisely this material has a memory in its parent stage, which is called austenite stage, which happens at a high temperature phase. So generally what we do is that we cool this material, so it comes to a low temperature phase or a martensite phase. Then you carry out all the deformations, and then whenever you will be heating it, it will go back to its memorized shape at the austenite phase. So that memory is called a shape memory effect. Now in some cases it can memorize both the austenite and martensite stage if you properly train it. So this case it is called one-way shape memory effect, whereas if you can properly train it so that both the phases it can memorize its shape, it is called two-way shape memory effect. So you can develop both the type of such shape memory effects. Now the materials which show such shape memory effect, it was first observed that in 1932 in gold cadmium alloy. Later on it was found that there are other alloys like ternary alloys of copper, zinc and aluminium, or copper, aluminium and nickel, or the best one is called nickel titanium. In fact, again Naval Ordnance Laboratory discovered it, so their name goes with the whole thing, and it is popularly known as nitinol today. So it's a particular ratio of about 45 to 55% of nickel and titanium which actually make this nitinol material, and it shows a very large shape memory effect. Now as I told you that this shape memory material has actually two different types of structures. In the austenite phase it has a body centered cubic structures. You can see the atoms at the corners and at the center of the body, whereas at the low temperature phase it has a face centered cubic structure. You can see that instead of just at the center of the body, there are these atoms which nicely comes into the center of the phases. Now something, if it is inside the center of the body, actually inherently makes it harder, and if it is a FCC, it inherently, the face centered cube is actually more flexible structure. The other thing to note is that at the BCC, in the austenite phase, these crystal structures of SMA is essentially cubic in nature, so all the lattices are equally dimensioned, whereas in the this case in the martensite phase it becomes tetragonal structure, so where you can see that the sizes are not the same. It would be different essentially. Essentially this direction it will be different in comparison to the other two directions. So this is what is the crystal structure of SMA, and why we go for SMA is that you get a large actuation stress, say for example something like 0.1 meganewton meter per kg in comparison to PZT. It gets about you can see here that 100 to 1000 times, in fact more you can get, some in between you can get for the SMAs, and also in comparison to human muscle also you can get a very high amplification, not as high as PZT, but still it is quite high. Okay, so once again you are coming up to 0.5 here, so it is slightly less than 100 times that you are getting through this. The strain is also very high, so essentially you are getting a large stress and strain out of the system, and that's what is very lucrative. And you can get this material both in wear form as well as in a spring form. Spring forms give a better actually stress and deformation, but the only catch is that the spring form is actually more complex to analyze, so modeling is little bit difficult in the spring form. Now if you look at this diagram very carefully, it actually describes the entire process. As you can see here that in this case we have the stress, 3 axis, strain and temperature. So let's say the material is first starting from this level when everything is 0. Now if I apply the stress, and to begin with let us say that it is at austenite phase. If I apply the stress, it will deform until beyond a point it will behave almost like a plastic deformation, and then if I reduce the stress, this plastic deformation will get reversed. Okay, so this can happen inside the austenite phase. But if you cool this material, let's say you are in the martensite phase, then if I increase the stress, it will then go to the plastic deformation, it will go to detwine martensite. I will once again reduce the stress. Now it will not go back to zero strain, it will be somewhere here, and then if you heat it up, only then it will come back to its parent phase. So that's what is the shape memory effect. And also the hysteresis in this effect, the stress-based effect, is also called superelasticity. So these are the two effects that is generally observed in the shape memory alloy. Applications, as I told you, is phenomenal. It is increasing every day. Mechanical, robotics, biomedical, civil structures and composite. Specifically for robotics, it is used in mini actuators, sensors, biomimetic robotic hands and crawler robots. So there are very many applications of the shape memory alloy today. Now here there are some examples, as I am showing you, about the SMA type of an artificial muscles which is joined using springs. You can see it in the two views. Now this can be used for developing the fingers. So those Asimo fingers, which is controlled by servo motor, can be in fact better controlled with less power with the help of SMAs if you can model it properly. And you can actually determine the forces there so that it doesn't get crushed. So depending on the type of element you are holding, you can control the force. So that is the beauty of the SMA actuated prosthetic hand. SMA is also used in terms of sensors. So there are not many applications, but we have devised some applications for SMA as sensors as well. You can see here is a SMA based sensor where there is a rotating drum which is having the contact end points, and these 2 points are connected with the help of styluses, and these styluses are operated by SMA wires. Now the moment the 2 styluses are on conductive tape, there is a current that will pass through, and as soon as there is a current that will pass through, there is a heating effect, and the switches A and B will operate so that you will get a signal out of them. And once one of the stylus will miss during rotation, it will not be able to operate, and hence you will see that the signal will come down to 0. So by measuring these 2 counter outputs, you will be able to find out how much of rotation is happening on this particular drum. Thus you can actually make a nice sensor, a very robust sensor out of it. The details of it is again available in one of our papers in sensors and transducers. Now you can also use these SMAs in terms of muscles. Let's say if there are 2 compliant links. So there are 2 links and I have attached them with 2 SMA wires, and you can see that by doing that you can actually very nicely manipulate the tip of this whole system. So this is a fabricated 2-link mechanism where SMA wire is controlling, essentially 2 SMA wires are controlling the 2-link deformation, and by that it is controlling this point of interest, the topology of this point, so that it can be used in terms of various types of manipulations, for example. So this is once again is reported in one of our paper in Journal of Mechanical Design. Now you can do very many actually different type of shapes you can generate to it. So here for example you can see that there is a figure of 8 that is generated by using the shape memory alloy based 2-link mechanism. In fact, one can actually find out that what kind of current through simulation will be able to generate it, and you can actually feed that same current loop into the system like this type of a system. You feed back the currents in the 2 SMA wires related to the 2 links, link 1 and link 2, and you will be able to get the desired deflection in the system. So this is this is one way of using SMA for developing nice manipulators which can be used for finger movements, things like that. Now it is used in general for control of aerodynamic surfaces, like for control of motion, for vibration isolation, for grasping of robotic fingers, space exploration, as filter, and for deployment of solar array hinges. Truly, too many applications. It is increasing day by day. What's the advantage? I'm just giving here a quick comparison. PZT, which was a piezoelectric material, its strain level is 1000. PVDF, which is a plastic piezoelectric material, let's call it, its strain level is 700. Tafenol D we discussed today has a strain level of 2000, which means it gives more strain than these two. Nitinol will give you about 20,000. It gives much more than all the three. Only thing is that in terms of elastic modulus, this one is little bit softer, whereas this one, Tafenol D and PZT, both of them are equally high in nature. And then from the bandwidth point of view, Tafenol D is the SMA is the smallest, then Tafenol D, and followed by the piezoelectric material. So this is just the conglomeration of the properties so that we can take a quick decision in terms of the use of the smart material. Now this is where we will put an end of this lecture. In the next lecture, we will look into another kind of a smart muscle, which is made of shape memory, which is made of electroactive polymers. Shape memory alloy we have discussed today. Thank you.